Last episode, we fine tuned a sentiment classifier and stared at a confusion matrix 4,380 true negatives, 120 false positives, 95 false negatives, 4,405 true positives. Those four counts TP, FP, FN, TN aren't just a pretty grid, they are the raw ingredients every classification metric is cooked from. Today, we take that exact grid and turn it into four numbers a human can actually read: accuracy, precision, recall, and F1. And we do it with one tiny Hugging Face library, whose whole job is computing metrics correctly, so you never have to remember the formulas. Here's the problem with the confusion matrix. Nobody can glance at four numbers and feel how good a model is. Is 95 false negatives a lot? Out of how many? Your brain can't normalize it on the fly. We need a single percentage, or better, a few percentages, each answering a different question. That's what metrics do. They squeeze a grid into a scoreboard. Accuracy is the obvious one. Of every prediction you made, what fraction did you get right? It's the diagonal of the matrix, true negatives plus true positives, divided by everything. Simple, intuitive, and dangerous. On a dataset that's 99% one class, a model that always guesses that class scores 99% accuracy while being completely useless. Accuracy alone lies on imbalanced data. Precision asks a sharper question. Of all the times you shouted positive, how often were you right? It's true positives over true positives plus false positives. High precision means when your model commits, you can trust it. Low precision means it cries wolf. If a false alarm is expensive, flagging a good customer as fraud, precision is the number you protect. Recall flips the camera around. Of all the things that were actually positive, how many did you catch? True positives over true positives plus false negatives. High recall means you miss almost nothing. If a miss is expensive, letting a real fraud slip through missing a tumor, recall is the number you protect. Precision and recall pull against each other. Crank one and the other usually sags. So which do you report? Neither alone. F1 is the harmonic mean of precision and recall, a single score that's only high when both are high. The harmonic mean punishes imbalance. If precision is 95 but recall is 5, the plain average is 50, but F1 collapses to 9. That's the point. F1 is the honest one number summary of a classifier, and it's what you put on the model card. And here's the beautiful part, you never compute these by hand. Hugging Face has a library called Evaluate. You load a metric by name, feed it your predictions and the true labels, and it returns the number, implemented correctly, tested, identical across every project on the hub. 4 metrics, 4 load calls, 1 combined dictionary. No formulas, no off by 1 bugs, no arguing about averaging modes. Let's go build it. One file zo7evaluate.py, 2 pages. Page 1 loads the 4 metrics and runs the predictions through our fine-tuned model. Page 2 computes every metric, packs them into one dictionary, prints it, and draws the bar chart you're about to see. No training here. We already trained last episode. This is pure measurement. Up top, the imports, we pull NumPy, the pipeline, and auto tokenizer from transformers to get predictions. And the star of the show, evaluate.load, we also grab matplotlib to draw the bars at the end. Then we set the model checkpoint to the classifier we fine-tuned last episode and point at the IMDb test split we'll score against. Next, we load the 4 metrics, evaluate.load accuracy, then precision, recall, and F1, 4 separate metric objects, each a tiny tested implementation living in the hub. Loading by string name is the whole interface. Evaluate fetches the right code, so accuracy means accuracy everywhere. We stash them in a list so we can loop later instead of repeating ourselves. Now we generate predictions. We spin up a text classification pipeline, On the fine-tuned checkpoint, run it over the test texts and map each predicted label, positive or negative, to an integer 1 or 0, so it lines up with the dataset's integer labels. Preds and refs are now two equal length arrays of zeros and ones. That alignment is everything. Predictions and references must be the same length, same order, same encoding. Page 2, the payoff. We call .compute predictions, preds, references, refs on each metric. Accuracy and recall take no extra arguments. Precision and F1 we pass average Hokosa binary, so they score the positive class directly. We merge all 4 results into one results dictionary with a dict comprehension, round each to 3 decimals and print it. That single printed line is the scoreboard, accuracy 0.976, F1 also 0.976. The last block draws the figure. We pull the metric names and values out of the dictionary, hand them to PLT@bar for a horizontal bar chart, and loop once more to stamp each bar with its value at the tip. Yellow bars on a clean white card, 4 labels down the left edge, values on the right. We tighten the x-axis to the 0.9 to 1 range, so the differences are actually visible, then save it to metrics.png. And that's evaluation, a confusion matrix in, 4 trustworthy numbers out, drawn as a chart anyone can read at a glance. Accuracy 0.976, precision 0.973, recall 0.979, F1 0.976, a genuinely strong classifier. Great scores, but this model is full size, every one of its 110 million weights tuned. Next episode we shrink what we trained down to a fraction of a percent using LoRA and watch the accuracy hold anyway.